How to predict the products of alkene addition reactions. In this lesson, we're going to work our way through 4 example problems, and we'll go through the different Regio selectivities, whether they're Markovnikov or anti-Markovnikov. We'll go through the stereoselectivity, whether they're syn additions or anti-additions. And then finally, we'll take a look and see how many chiral centers are formed in these products and use that to predict how many products actually form. Now, this lesson is part of my new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notification. You'll be notified every time I post a new lesson. So finally, I want to finish off these alkene addition reactions by just working a few examples, predicting some products, and showing how we predict the number of products based on how many chiral centers we formed, this sort of thing. So if we look at this first one, we're adding HBr to an alkene, and you should remember that HBr is one of the 3 reactions that goes through a carbocation intermediate, and you're definitely going to want to draw out that carbocation intermediate. So in this case, we're going to add the hydrogen to the less substitute side and end up with a carbocation on the more substitute side, which in this case is tertiary. And the 3 adjacent carbons are secondary, secondary, and primary. This one's not going to rearrange, and that's ultimately where the bromine is going to end up, right where that carbocation is. And so we added the H to the less substitute side, the bromine to the more substitute side, because this is the Markovnikov addition of H and Br. Okay, cool. Now I'll examine where we added the H, and so had a chance of becoming a chiral center, but definitely doesn't have 4 different groups. So in this guy here also doesn't have 4 different groups. And you might think at first inspection, maybe he does. So, but he's got a methyl, he's got a bromine, and then these 2 CH2s look similar. They still look similar, and they meet in the middle, and they're exactly equivalent. This thing's actually got a mirror plane of symmetry right down the middle here, and so no 4 different groups for him either. He's not a chiral center. So out of a chance of forming 2 chiral centers, we didn't form any, and we get 1 achiral product. We have no stereochemistry to show whatsoever. Now, if we do the same reaction but with peroxide now it's going to go anti-Markovnikov, and you're going to see this is going to be a pain in the butt. And so in this case, we don't have to worry about rearrangements or anything, but it's going to go anti-Markovnikov. So the more substitute carbon got the hydrogen, which is not drawn in, and the less substitute carbon got the bromine. And now we have a little bit of a problem because we formed 2 chiral centers. Where the hydrogen added, 4 different groups. Where the bromine added, 4 different groups. 2 chiral centers, that's when your stereoselectivity matters. And for HBr and peroxide, it doesn't have any stereoselectivity whatsoever. And so that being the case, you not only get the 2 syn products, you get the 2 anti-products, and you get all 4 possible stereoisomers. And so in this case, this would not be a sufficient answer, and maybe I need to do something like this. Let's make sure we get our 5-membered ring correct. Cool, so we get 4 different stereoisomers here. So these 2 are a pair of enantiomers, and these 2 are a pair of enantiomers. These 2 resulted from syn addition. These 2 resulted from anti-addition. And in case you think I just misspoke, so keep in mind that what syn and anti is relative to the hydrogen that wasn't drawn in. And the H and the Br are both wedges here, and they're both dashes here. That's syn addition. And here, so the bromine's on a wedge, the hydrogen's on a dash, that's anti-addition. And here the bromine's on a dash, the hydrogen's on a wedge, and again, that's anti-addition. So again, it's always relative not to the 2 groups you can see drawn in, but the 2 that actually got added across the alkene. So pain in the butt, first example we saw where you get all 4 stereoisomers. So it's difficult to actually write a question where that happens, but it does show up on occasion, just like it did here. Cool, this next one, Br2 in CCl4, and you might recall CCl4 is one of your classic inert solvents, and so this is just going to add 2 bromines across our alkene here. Cool. And unfortunately, where both bromines added, we formed 2 chiral centers. And again, that's when your stereoselectivity matters. And for halogenation, so we form that 3-membered ring with bromine, and the carbons we attack are sp3 hybridized, so we have to do backside attack, and it results in anti-addition. And so in this case, this is not sufficient. We've got to show that these 2 bromines are on opposite sides here. So if one's a wedge, the other's a dash, but that means we got to show stereochemistry all the way around. That would, if this bromine's a wedge, that means this methyl group's a dash. And if here the bromine's the dash, that means this methyl group's the wedge. And then we draw the enantiomer as well. Cool. Pair of enantiomers yet again. So form 2 chiral centers, but it's anti-addition, so we only got the 2 anti-products. And finally, this last one is very similar to one we already kind of worked out. So in this case, we're going to add 2 hydrogens across the alkene. And when we do so, it reduces it simply down to an alkane. And in this case, where the 2 hydrogens added, both are chiral centers. When you add when you form 2 chiral centers, we typically need to know your stereoselectivity in that one example. And in this case, it's syn addition. So instead of expecting to get 4 products, we only expect to get the 2 syn products. However, due to symmetry here, so being syn, we could think, oh, it's both wedges or both dashes. So if I make the both methyl groups wedges, that means the 2 hydrogens are on the dashes. But if you think you got to draw the other, we got to see, oh, there's a mirror plane of symmetry in this. This is a meso compound. And whether we put the 2 methyl groups on both wedges or both dashes, it's exactly the same thing. And so one of those unusual examples again, where instead of getting 2 products like we expected with syn addition and 2 chiral centers formed, we only get a single meso compound. Now, if you found this lesson helpful, consider giving me a like and a share. A couple of the best things you can do to help promote the channel. And if you're looking for the study guide that went with this lesson, or if you're looking for practice problems on alkene addition reactions, check out my premium courses on chadsprep.com.